your screen. Okay. And this bell-shaped distribution, sometimes people call it normal distribution. Sometimes people call it Gaussian distribution. The Gaussian is a famous mathematician, right, who actually came up with this model. Okay. Now, earlier in the first few chapters, we talked about descriptive statistic, and what we did is we collect data, right, and we've gone through different type of methods to organize these information. For quantitative type of variable or type of data, what we do, we make a frequency table, right? We first define classes. Usually there are a range of numbers, right? And then we convert that table to a relative or frequency histogram. What we're trying to do is understand the distribution pattern of it. And I said that it's important to understand the distribution pattern, knowing that whether it's a bell shape or skewed to right or skewed to the left, okay, or it's bimodal, or is there any outliers? Now, this chapter we're talking about when you have a bell-shaped distribution, how mathematically we can use so-called probability density function for a bell-shaped curve. It's a mathematical function, right, that people come up with to categorize this bell-shaped curve or describe this bell-shaped distribution. So in the future, if we're interested in estimating any kind of percentage, right, related to this distribution, right, we can do it. Okay, so we're going to use some mathematical model to actually help us to describe this distribution, so that, well, when you report to people, you can just report to people that, well, for this variable, I have mean is this much, standard deviation is this much, and I also tell you, well, the distribution is bell-shaped. Then people would know a lot about this distribution, and you will know why, okay, from this chapter. Okay, so now if you made histogram, this would be kind of like, if it's a bell shape, like the histogram may look like this, right? Symmetrical bell shape, that's what I meant. Okay. Now mathematically, we'll try to come up with some kind of curve, some kind of smooth function, right, to describe this kind of distribution. In this course, we're going to learn that. Okay. And this curve or this function, we call it density function. How the density of your data distributed, right, by using this mathematical formula. We call it probability or distribution density function. Okay. And people actually develop theory, right, behind this. So we don't need to worry about those theory, right? We just want to take the result of this modeling techniques, right, and then we make use of that to do many things. In fact, from now on, you're going to see a lot of this distribution, normal distribution, in statistical inference, especially. Okay. So as I say, this probability density function is a mathematical model that we use to describe such a distribution, right? Bell-shaped symmetrical distribution. And this, since it's bell-shaped symmetrical distribution, it's symmetrical. So the mean, median, and mode will be all in the same location, right? That's a special property of this specific distribution, bell-shaped symmetrical distribution. Okay. Mean and median and mode, they will be at the same place. And this particular probability, we call it probability density function or distribution density function. Theoretically, right, both sides goes to infinity. Left side, this curve extends to negative infinity, and the right side extends to positive infinity. That's just in theory. When we really apply to data, right, some of the data only take on positive number. But again, this particular curve, a lot of times can help us to describe any kind of data, right, that are bell-shaped distributed very well. Okay, and we can make use of that to help us to do some sort of approximation and help us to get more idea about this distribution. Now, if you remember, I think you remember that Chebyshev's rule by the name, right? Remember that Chebyshev's rule? That we use that Chebyshev's rule, right, to help us to get an idea about distribution of data if we know the mean and standard deviation. We also learned an empirical rule. We say that if you know the mean and standard deviation for a bell-shaped distribution, then we know that about 68% of distribution within one standard deviation, and 95% within two standard deviation, and 99.7, almost 100% within three standard deviation. How do we know that? It was because of knowing or having this so-called bell-shaped probability density function that we're using, right, for help us to approximate these distributions. Okay. Of course, before we can use this particular function, we have to, check whether this function really model our data very well or not. And in the lab, I mentioned to you a normality test. Okay. That's a test that we can use to help us to check, well, what data can be assumed normal. If data can be assumed normal, if you know the mean and standard deviation, then you can use a technique that we learned here to help us to approximate the distribution of data in any specified range, not just within 1 or 2 or 3 standard deviation. Tell me 2 numbers, tell me an interval. I can use this method to approximate the distribution in that range. Okay, that's how great this thing is. And there are also other things that we're going to use this for. Okay. And the 4th property is just telling you within 3, but you know within 2 or within 1 or within any range, I'll be able to find that out. Okay. And why can we do that? Well, because this is a mathematical formula. And it takes people who know calculus to be able to actually make use of this so-called probability density function to help you to approximate the area of a percentage. Okay. This function looks so ugly, right? But let's not worry about it. This is just telling you that there is a mathematical formula there that we can use to help us to approximate this distribution. But you don't have to know this, okay? We're going to have a table to help us to actually figure out how to find these percentage or approximate these percentage without using this. Indirectly, right? Indirectly, we're using this, right? But everything is in the table. Information all in the table. So you don't really need to use this density function to actually do any calculation. I just thought you know it, right? There's a formula there, okay? And this formula depends on some parameter, sigma. Sigma really is the standard deviation. This mu here is the mean, okay? So this expression or this function is function kind of determined by mu and sigma, okay? This is just telling you that this bell-shaped normal distribution, the behavior of this distribution really depends on mean and standard deviation. If you know the mean and standard deviation from this bell-shaped distribution, then you will know everything about this distribution. So people say that, well, if mean and standard deviation completely help us to describe the distribution, the bell-shaped distribution. If you know mean and standard deviation, you know everything about this distribution. And gradually you will know why, okay? Now, often people use this notation, n stand for normal, n parenthesis mu and sigma. Sometimes people use mu and sigma squared to denote that there's a normal distribution. Mean is this mu, and standard deviation is this sigma. If they put sigma squared, then that means what? The variance of the distribution will be that sigma squared, right? So they will use an n in parentheses and put 2 numbers in there to denote a normal distribution. So for instance, if I tell you that I have a normal distribution that's 72, 5, using my notation earlier, first one is mean, second one is standard deviation. So this is telling us we have a normal distribution with the mean 72 and standard deviation 5. Okay, so this could be maybe a distribution for pulse rate, right? The average is about 72 and the standard deviation 5. Okay, you can use that to describe test score. Maybe it's after certain tests, right? You find out the average is about 72, but what's the measure of spread, right? Is 5, and the data just fit a bell-shaped curve very well, all right? So sometimes people just tell you, well, the distribution of the score can be described using this notation. Different professor does it differently. Right? When they say curve, they may use all different things. Sometimes many professors actually use a normal curve, right, to transform all these data, to rescore all the scores, okay, so that we only few maybe failing grades and only few have A's and most of them in the middle, right? Sometimes people use that. Yeah, you can do that. And of course, if I say n 130 and 24, this notation stands for that I have a normal distribution with a mean 130 and standard deviation 24. Okay, and you may be using this notation for maybe describing weight, right? Weights of certain group of people, average is 130 and standard deviation is 24, and it's bell shape. Right? And then when I want to describe that distribution, sometimes I may use a notation like this. So if you see a notation n and 130 and 24. Right, that may mean that we have a bell-shaped distribution with a mean 130 and standard deviation 24. Right, so that's just a notation, okay? And mostly you see that in the research paper or textbook, okay? In usual report, in application, usually people don't use these notations. People will just tell you, oh, I have a data, all right? Or I have a population mean is this and standard deviation is this. That's it. And maybe they tell you, well, this distribution is somehow like bell shape, okay? Now, here I give you actually 3 distributions. Okay, there's A and B they're all bell-shaped distribution, but these two things have the same center. Okay, so these two distribution mean are the same, but the spread seems like different, right? A is flat, B is much sharper, which means that mean will have a smaller standard deviations, right? So most of data gather closer around the center. Okay, so A and B, these two are all bell-shaped distribution, but they have the same mean but different standard deviations. So the shape will be like this. Okay, what's the difference between A and C? A and C have the same shape, yeah, but the mean are different. Okay, and B and C, they have different shape. No, actually, I shouldn't say shape, but spread. Okay, B and C, the spread are different, and mean also different. Okay, now there are so many different variables that we can observe, the quantitative variable that are probably bell-shaped. Each one may have a mean, different mean, and different standard deviation. Okay, earlier I mentioned to you that we can have a table to help us solve those problems. Okay, in fact, how do we solve this problem? We actually use the area under this so-called probability density curve to help us to solve a distribution problem, because the area under this curve, mathematically, we use the area under this curve to describe the distribution. Okay, over here in this area, in this range, you have more area under the curve because the curve is higher, right? And in these places, the area under the curve is smaller, means what? There are fewer cases over here. Okay, and so in fact, if I have a situation, I wish to find out, I have a bell-shaped distribution, and I know the mean and also the spread. Okay, I wish to find out what the percent of distribution between these two numbers, C and D. Mathematically, I will try to find the area under this so-called probability density curve in between these 2 points. So it'll be this area here. Okay, that can help us find the probability or percentage of distribution in between C and D. Now, however, this is a strange distribution. Even you know calculus, right? You can't do it by hand to solve this problem. You have to rely on computer. So even you are very good with calculus, right? You know calculus and you're very good with calculus. You can't solve this problem by hand. You have to rely on computer or the table, right? So no matter how good your math is, right? Everybody's going to look at this table, okay, to help you to solve the problem. And we're going to see how we do that, okay? So it is actually the area under the curve, under this density curve, that we use to represent the percentage of probable distribution. Okay, and we will see a lot of example there. Okay, now because this is actually area that we are concerning, right? So when you're talking about percentage between these 2 points A and C and D, including the endpoint or not including the endpoint, it's the same thing, right? Because there's really no area on this one line there, right, on the edge, right? Am I making sense? Okay, so I ask you what percent of distribution between is greater than 60 and less than 70. And it's the same as percent of distribution that is greater than or equal to 60 and less than or equal to 70. Right. Having endpoint included or not, the result is the same. That's the first thing I'd like you to know, because it's really the area under the curve representing the percentage, right? Including endpoint or not including endpoint really doesn't make any difference because there's no area on endpoints, okay? So that's one thing I'd like you to know. And I also mentioned to you that there are all kinds of normal distribution. When you change the mean, change standard deviation, you have different normal distribution. And we can't possibly make tables for all these different distributions. So how can we do it then? We start with this so-called a standard normal distribution. If you know your standard normal distribution very well, then you can use the table with the idea of standard normal distribution to help you to solve any kind of distribution problem. Okay, so we'd like to start with this so-called a standard normal distribution. What is standard normal distribution? It is a specific normal distribution that has a mean 0 and standard deviation 1. If you have a normal distribution, bell-shaped symmetrical normal distribution whose mean is 0, standard deviation 1, and that distribution is called standard normal distribution. Okay. Again, this normal distribution, if you try to draw a curve, it's a symmetrical bell-shaped curve. And its point of symmetry, the center point, I usually call it, right? The center of gravity is the location of mean. Okay. So if I ask you to draw a bell-shaped distribution, tell you the mean, you'll be able to just draw a symmetrical bell shape and mark the center as the mean of the distribution. That's it. Okay. And usually people use a Z notation, Z, to stand for standard normal variable. Okay. Earlier I used X equal to something when I'm dealing with a binomial, right? But when we deal with standard normal distribution, we usually use a variable notation Z. Okay. So this Z has a normal distribution with a mean 0, standard deviation 1. So if you see an n parenthesis 0, 1, that means a standard normal distribution, a notation for standard normal distribution. Okay? Good. Okay, and then we use cap later usually to denote the whole distribution, right? Like when we do binomial, we use a cap x, right? And if cap x equal to some little x value, right? That's the way we actually write down the formula, right? But I guess it doesn't really make much sense, right, to you, I guess. So you don't have to worry about it. Just knowing that the z is a notation we use for standard normal distribution, right? And we're going to use x for any other regular normal distribution. Okay? So I mentioned to you that there's a table, right? Actually, that table is called standard normal table. It's a table that can help us to find the area under the so-called standard normal curve. And remember I said that area under the normal curve represents the percentage, right? So if you know the area from 0 to some point z, for instance, then you know the percentage of distribution in the standard normal distribution that is in between these 2 points. And the standard normal table actually can help us to solve that problem. Find the area under the curve, okay? Again, remember the area under the curve represents the percentage or probability if you're dealing with probability problem. And of course, this total area under the curve will be what? Since it represents the probability, the total area under the curve is total probability, right? Is 1 or 100%. Okay? That's how people actually set up mathematicians set up this so-called probability density function. All the probability density functions, or all these probability density curves, have the same property that the total area under that curve is equal to 1, right? Or total area under the curve is 100%, right? Or 1, okay? So how do we use this table then? Let me see. That's actually the back on the front cover. This is the standard normal table, okay? What this table gives you is the total area under the standard normal curve, okay, between 0 to some point away from 0 to the right. Okay. Now let me show you this thing here. And you also have a formula card, I believe, right? That has this. Where's my formula card? My formula card is actually over here. Your book comes with a formula card. This formula card also has that standard normal distribution. Let me show you. Maybe this formula card looks better. Okay. This formula card, it gives you this chart. That's just telling you that, well, this chart tells you the area in this kind of shaded area, area under the curve from 0 to some point z. Okay. Now then let's look at this table itself. This table, standard normal distribution table, top row and the very left, this left column, right? These are reference for the z value. For the z value like this, okay? And over here, this part tells you the area, this kind of shaded area. Okay? And this is a reference for this z-score. And this tells you that, well, if you have 2 decimal places, what's the second decimal place like? And this first column gives you the reference for z up to first decimal place. So if I wish to find the area under this standard normal curve from 0 to, let's say, 1, z-score is 1. 1 is 1.00, right? So I come to this table, look for the value 1, and first decimal place 0, second decimal place also 0. So this 1.00, this number 0.3413 is the area under the curve from 0 to 1. All right? From 0 to this area under the standard normal curve from 0 to this z-score, 1.00 is 0.3413. Of course, then you have z-score cover up to 3.09. So if you have a z-score over here that is less than 3.09, you'll be able to find the area under the curve, right, from 0 to that point. Okay? So that's what I mean. Right? If you want to find the area from 0 to some z-score, right, the percentage from 0 to some z-score, you can use a standard normal table to help you to solve that problem. Okay, so let's look at another example. If I wish to find the area from 0 to some point that is 0.32, And you look up a z table, standard normal table. For this first column, look up 0.3, since first decimal place is 3. Second decimal place is 2, right? So this column and this row, 0.1255. That's the area from 0 to 0.32. Okay? Make sense? It's pretty simple. It's not hard. You just saw a formula that's so complicated looking, right? But actually, if I'm solving this problem with the table, it's so easy. Okay? Am I making sense? Let's look at another one. Still the 0.32. This time I'm talking about what percent of distribution that is higher than 0.32. That means what? Remember, this curve describes the distribution. I'd like to know the distribution above 0.32. That means what? Everything above it. Right? The area above 0.32 under the standard normal curve is the percentage of distribution. It's the standard normal distribution that is above 0.32. Okay? Now I know the area from here to here. I just found it. That's 0.1255. Now this is a symmetrical bell-shaped curve. If it is symmetrical bell-shaped curve, what area will be to the left of 0? How much is to the left of 0? 0.5, right? How much to the right of 0? 0.5. Now, if I know the area from 0 to 0.32, of course I should know this tail area, right? I say it's 0.3745. How do I know that? This piece is 0.125. Total area to the right of it is 0.5. I just use 0.5 minus this piece, right? I get the 0.3745. That's this tail area. Does it make sense? So let's say if I give you a test, I give you a very weird type of scores, right? And then average score is 0, and there are some negative score and positive score. But the score distribution is bell-shaped with the mean 0, standard deviation 1, which is standard normal. What percentage of people score higher than 0.32? But since the area above it is 0.3745, so there are about 37.45% of a student whose score is higher than 0.32. Okay? So I can use this normal curve to help us to approximate the distribution of data or scores in any specified range. I think you gradually realize that, right? Just now I just found what percentage is between 0 to 0.32. Now I also found the area above 0.32. And that's also the percentage of score that is higher than 0.32 if the score follows a standard normal distribution, if all the scores. Okay? Make sense? Okay, let's look at another one. How about what percent of distribution that is less than 0.32? If my score is standard normally distributed, and I wish to find out what percent of the scores that are less than 0.32. That means what? Everything below 0.32. That could be negative. Okay, so that's everything below it, and that shouldn't be too hard, right? We use a table. We find out what is this piece. But what we really need is everything below it. So what we do? We know how big is this, right? This is half of the distribution, 50%. Yeah, 0.5 plus this one. You get 0.6255. So the percentage of a score that is less than 0.32 is what? About 62.55%. If the distribution of these scores follow a standard normal pattern. Okay? So this table actually helps us to find the area under the standard normal curve in between 0 to a certain point, right? And remember that area, again, represents the percentage. Okay, so if you do have a score that has this type of distribution, you'll be able to find the percentage distributed, right, in any specified range without problem, right? We have gone through 3. How about this one? Again, I have some test score follow standard normal distribution. What percent of the distribution between -1 to +1? If you have a table, look up the table. What's the z-score? Or the area, area between 0 and 1. We know that area between 0 and 1. You look up a z-score, 1.00, that's 0.3413. So you know the area from 0 to 1, okay? 0.3413, right? Now, that's area from here to here. But what about area from here to here? You say, well, there's no negative score in the table. Well, we don't need that because this curve is symmetrical. So if you know the area from 0 to 1, you know the area from 0 to -1. It's exactly the same. Okay? So the area from 0 to 1 is 0.3413. Area from 0 to -1 also 0.3413. Add them together, what do you get? 0.6826. Okay? So if you have some kind of test score that follow standard normal distribution, maybe this is bone density test score, right? Follow standard normal distribution. And what percentage of people who test score is between -1 to +1? About 68%. Now, if you recall that empirical rule, what percent of distribution lies within one standard deviation? 68%. That's how they get that 68%, within one standard deviation. Okay? So this kind of shows you why the empirical rule says 68%. That's because of this. Okay. Now, could you find out if this is -2, this is +2, how big would it be if you have the table? Let me also show you the table here. What percentage will be within -2 to +2? If you look at the table. Yeah. If this is -2, this is +2, you first want to find this, right? If you know this, then you know this. But what is area from 0 to 2? 0.4772. So this is 0.4772. So this piece also 0.4772. Add them together, you get 0.9544. Isn't that just around 95%? Okay? Remember, empirical rule says that there are about 95% of a distribution within 2 standard deviation. Now, what's a standard deviation for standard normal? 1, right? So -2 to +2 is really just a 2 standard deviation of the mean, and that's about 95%. So I guess you can find out what percentage in 3 standard deviation, right? Just look up z-score 3, right? Multiply that by 2, you get the percentage within 3 standard deviation. Okay? Now it makes sense. Why empirical rules say it that way? Or how do they know it? Right? This is why. Okay. Okay, let's look at another one. This one, we want to find the percentages distributed between -1.4 to +2.33. How do we do that? Now this one, you have to divide and conquer. Right? You find out what is area from 0 to 2.33. You can also find the area from 0 to -1.4. If you find those two pieces, you add them together. That's total percentage, or total area from -1.4 to 2.33. Right? So what would that be then? If you check this table, from 0 to 2.33, that's 0.4901. Okay. If you look at the table, 2.33, 2.3 and 3, right? 0.4901. I hope you can see that, 0.4901. This number, right, 2.33. Okay? And then from 0 to 1.4, 1.4 is right here, 0.4192. Okay, the second decimal place is 0, so that would be this column. And add those two numbers together. You get the percentage distributed from -1.4 to 2.33. And that's about 91%. Okay, that's easy, right? So that formula is really nothing. Don't worry about that formula. Even if you know that formula, it can't help you to do anything. Really, this table is really the key. It's everything. Okay, but you know that formula actually is a formula that people use to produce this table. Okay, so I'd like you to know that. Okay. 5 minutes. How about let me give you some practice? Maybe one question to play with. Okay. But there are a lot of exercise problem in the book. I like to practice a lot on this. This is something that you can definitely get, but you just have to practice. So, how about this? How about finding this? The distribution, right, for the standard normal, right, what's the distribution? It's between negative 1.11 to 1.25, positive 1.25. Copy it down, and I'm going to put the table on the screen, okay? So first copy this down. You got that? Okay, and I'll put this. Are you ready? Okay, so I'm going to put this table here. What my question? 1.11. That'll be good. I'm going to collect it, right? That's a good idea. 1.11 and 1.25. You should have those information in this part of the table. Okay. So what? This? Okay. This is a question, okay? I guess you all got it, so let's not worry about it. Okay, good. Oops. This is easy, right? Yes. Is it too easy? No. Let me give you another one. Give you another one. I like that. I think you like that too, right? Okay. Let me give you another one. How about change it to this? That probably will be also too easy, but anyway. You have all the number there. You really don't need a table now, right? But I will pull it out again and let you look at that. Now, when you solve these type of problems, I'd strongly recommend you draw a picture. Draw a standard normal curve. Okay? Every time you're solving these type of problems, draw a standard normal curve. How to draw a standard normal curve? First, this horizontal line, put a bell-shaped curve. That's not complete yet. Standard normal curve has a 0 here. You have to mark that 0. Okay? And then start marking these events, right, to help you to realize what's happening. Okay? That's very important. Making a curve and then mark these points. These are all positive, so these points should be all to the right, right? There's a negative and positive, so you have a point here and a point here. And you want to shade that area, right, to know which kind of area you're looking for, and then you'll be able to solve it. Okay, so let me give you this again. Again, what these numbers are. These numbers are area under the standard normal curve from 0 to the reference z-score. Okay, any of these z-scores. Remember this one? Let me give you another example. For those of you still kind of confused. If I wish to find out area from 0 to 0.21, okay, that's this area. So your z-score is this, okay? You come to your table, z is 0.21, second decimal place 1, that's 0.0832. That means this area is 0.0832, okay? This column, combine this column and this row, right? You have that z-score, right? This gives you the reference for z-score up to the first decimal place. This gives you the reference for z-score up to second decimal place. For 0.21, that's 0.2, and second decimal place is 1. So the area, this 0.0832, is this area here. That's how we use this table. Yes?
All right, I was going to ask, do we subtract all these?
Okay, sometimes you will subtract, sometimes you will add. That's a good question, okay? If you have a situation like this, or like this, you got to add these two, right? From -2 to +2. What if I have a situation like I want to find out area from 1 to 2? Then what should you do then? You know the area from 0 to 1, right? And you also know the area from 0 to 2. But you wish to find out this piece. What should you do then? Use this piece, subtract this piece, and you will get this piece, right? So you will have to subtract. Okay? Does it make sense?
Yeah.
Okay. Okay, so that's just these two questions. Okay, that's it. If you finish, write your name there, and we will look at this table, right? Yeah.
So we're just interested in this piece. I did it too when I used to verify it.
Why do you do this then?
Because I just verified that I did this. I was verifying my answer.
Oh, you're taking two different approaches to solve this
Yeah,
problem.
two
This should be the way you do it, right?
But I did two approaches so I could theoretically verify it.
Okay.
That's it. But that's the easy way. But
Yeah.
okay.
Good.
For change.
Questions? Any question? Anybody still confused? Anybody still confused? Let me give you another one. What if I want to find the area from 0.21 to, let's say, 0.33? Let's say. How do we do this?
You want that on the paper too?
No, this is not. This is just another example. If you have 0.21, that'll be here, right? 0.33 is a little bit higher. But I'm interested in this area. And how do you find that out then? Well, you know the area from 0 to 0.33, right? What would that be? 0.33. That's 0.1293. That's from 0 to 0.33, okay? You also need to know the area from 0 to 0.2. 0 to 0.2, that is, 0.21. 0.21, that is 0.0832, okay? 0 to 0.33 is this. 0 to 0.21 is this. What's the area in between then? The difference. So if you can find a difference, that difference is this area here. Okay? Does it make sense? Area from here to here, that's this. Area from here to here, that's this. But you want to know this piece. Use that bigger piece. This bigger pizza, subtract the smaller piece of pizza, that's the remaining pizza, right? That smaller one, okay? Okay, that's it for today. Right? Okay. If you know